Okay, so chapter 12 is about thermal energy and thermal expansion. Probably one of my favorite chapters. I find thermal expansion kind of fascinating. Um, Basically, it's how much something changes in size based off of temperature. Because we know that if you you can't open a jar. So if you run it under hot water, it'll expand it and allow you to open the jar. Um, Anyways, kind of some neat implications of that. You'll kind of see that here in a moment. So let's start with the equation. It's really just there's no proof of it. It's just a percentage change, and this is the equation for linear thermal expansion. Your delta L will be the change in length of said object. Your alpha is your coefficient of linear expansion. And unlike the coefficient of, say, static friction, it does have a unit. It's per degree Celsius. Sometimes you'll see it written as this Celsius to the negative first, since it's the same thing. Let me put a little or here. I'll use the or symbol. There, or. Um, L naught is your original length, since it's not. OG length, and of course delta T is your change in temperature, since we're dealing with temperature changes. And you've seen this before. Number one, this is the little grates that you see on roads. Basically, they allow the concrete to expand and contract based off of the temperature or the season. In the summer, you'll see the little teeth far apart, in the summer you'll see them really close together, and in the winter you'll see the teeth really far apart, fall. It's funny. Another example is when you don't account for that, you get warped tracks, like in this picture right here. Um, they'll tend to warp over time, or just simply because you did not allow in this case, your steel to expand and contract back and forth. So, um, so two little examples of thermal expansion that you see in your everyday life. So let's do a problem. The Mackinac Island Bridge has a total length of around 8,038 meters. It's like 6 miles long ish. The average minimum and maximum temperatures in that area are 10 and 76 degrees Fahrenheit. So basically, the lowest temperature you'll find it's in Michigan. Sorry, I didn't tell you that. Is around 10 degrees, and the highest temperature you're going to see is around 76. So really nice weather there. What is the change in length of the bridge from winter to summer? And the coefficient of linear expansion for concrete is 12 times 10 to the negative 6 per degree Celsius. So our equation is delta L equals um, alpha L naught delta T. We want to see the change in length, so we're just solving for delta L. So simple little thing there. So our alpha is going to be 12 times 10 to the negative 6 per degree Celsius. And our original length is 8038 meters. And our change in temperature, that's what I'm going to have to convert. So I remember now. I need to convert that to Fahrenheit. How do I do that? So I'm just write delta T for now. Well, a couple ways, but the way I usually remember it is that um, Fahrenheit is equal to 1.8 Celsius plus 32. Um, Different ways of doing it, but that's what I always remember. And so if I want to find it for Celsius, I can find it for each one. And so I'm just going to plug that into my calculator, because I think most of you should know how to do this already, but that's kind of a reminder. So I take my 10, subtract my 32, and then I'm going to divide that by 1.8, and that gives me a negative 12.2. And then my other temperature is going to be 76 minus 32, and then divide that by 1.8, and that's going to give me 24.4. I did not give this to you in Celsius because there are a couple. I think I usually give you a couple problems on the very first part of this chapter, which is just conversions. And you've seen it before, I know at this point, so I generally don't cover it, but I did it in the first problem, so at least I say that we did some of it. Well, anyways, scrolling down here, that's going to give me a delta L is equal to, I'm going to write this, 12 times 10 to the negative 6 per degree Celsius, and then I'll put my delta T here. So that's 24.4 minus a negative 12.2. And I forgot my little degrees Celsius here. And I wanted to put them next to each other so I can show you that Celsius cancels. And then I'm moving my L naught out front, and that's 8038. All right, let's do that. So 24.4 plus the 12.2, and then times 8038 times 12 times 10 to the negative 6. And we get a pretty large number. 3.5 meters. So, I mean, it's a very long bridge. It's over 8 kilometers long. So they're going to need a lot of those little grates that you see on bridges to allow the concrete to expand back and forth so that it doesn't buckle the bridge. So that's kind of one of the more interesting aspects of thermal expansion. And so if you look at some other bridges, like the causeway over Lake Pontchartrain in Louisiana, that expands by like 45 feet or something like that. And so they kind of have to keep that in mind whenever they're building, well, any object, but in particular bridges in this case. I'm kind of doing a slightly different problem here. So let's go to Minnesota. We have a Minnesotan with a hair length of around 2 meters. So I just kept it simple, 0.61 meters, 2 feet, sorry. And the coefficient of linear expansion for hair is around 34 times 10 to the negative 6 per degree Celsius. It's hard to find an exact value. So let's say what will be their hair length if they leave a building at room temperature to the outside. So basically these are real values that you would actually find, say, in Minneapolis. And then we're going to figure out how much pressure they would have to apply to their hair to make sure that the length stays the same. Anyways, so let's do that. Okay, so we're looking for something similar. We want to figure out the hair length, but first we need to figure out the change in hair length. So that's still going to be my delta L is equal to L, sorry, I'm going to write it the way I did it first. Alpha L naught delta T. Delta L is what we're going to look for at first. We know our alpha is going to be 34 E negative 6 per degree Celsius. L naught is the 0.61 meters. And then delta T. So we're going to go cold. So negative 24 degrees Celsius minus 23 degrees Celsius. Okay. Now this will give me the change in length, not the overall length. So negative 24. Yeah, that didn't work. Negative 24 minus 23, and then times that by 0.61, and then times that by 34 times 10 to the negative 6. And you get around negative 0.001. Rounded. 1 meter, which equals around negative 1 millimeter. So nothing that you'll ever notice. I mean, if you did, that would be kind of a big deal. But it actually is measurable enough for somebody that happens to go through that kind of temperature change. Well, all right, so now that's only the change in length, and I said I wanted to know their hair length. And so really, I just need to subtract the 1 millimeter from it. And keep in mind also this is negative to show that the hair is getting shorter. So it makes sense. And so it's going to be 0.61 minus 0.001. And that's going to give me a really small 0.609. So not a lot. Not really noticeable, but measurable. Now, to answer part B, we want to figure out the pressure they need to apply if we know that the modulus of um, elasticity for that is going to be 5 times 10 to the 8th newtons per square meter if we want to make sure it's going to stay the same length. All right, so this is kind of from last chapter, but if you recall, F over A is equal to E delta L over L. Okay, so we now know our delta L, we know our L, and we know E. We don't know force or area, but remember force divided by area is pressure. So I could instead change this to a P, and we could just simply solve for pressure. And that's what I'm going to do. All right, P equals 5E8 newtons per square meter. Delta L was the 0.001 meter over 0.61 meters. So 0.001 divided by 0.61 and multiply that by 5 times 10 to the 8th. It's going to give me a very high value, around 800 and, I'm just going to round it, 20,000 pascals. Or roughly 820 kPa. So quite a lot of pressure if you want to make sure your hair is going to stay the same length. That's value is probably a little bit off. That's the best value for the elasticity that I could find. But I never could find a really true value. But the problem is still the same, at least. The process is. Now, volumetric thermal expansion is similar, except you're expanding with respect to volume. And the other small difference is instead of an alpha, we have a beta, which is your volumetric expansion coefficient. And these are all in your book, by the way. There's a whole table of them. Volumetric expansion coefficient. All right, next. All right, so let's do a problem. So years ago, there was a lawsuit once gas prices shot up by Florida residents saying that they don't get, I think it was done by the Attorney General of Florida, basically that they're not getting as much gas than, say, people in the northern states because gas is sold by the volume and not by the mass. And since it's sold by the volume and we know that things expand or contract based off the temperature, when it's warmer, they should be getting less gas. Keep in mind the gas is kept underground. So it'll be regulated to some degree. So this would be assuming that it's actually just sitting outside. In which case, we're going to figure out the price difference between Yuma, Arizona, where it's around 63.8 degrees Fahrenheit, I believe is the average temperature. And then comparing that to Minneapolis, Minnesota. These are winter temperatures, by the way, 11 degrees Fahrenheit. On an average day in January, if your tank is 15 gallons and the price of gallon is gas is around $2.75 a gallon. And the coefficient, oh, that's supposed to be a beta of gasoline. I have not caught that over multiple years. And no one's ever pointed that on me. So, okay. So we need to figure out our expansion. So let's do that. So that's delta V is equal to beta V naught delta T. We know what delta T is, we know what beta is, and we know our initial volume. Now, you're thinking, oh crap, it's in gallons, we're going to have to change it. Well, luckily for you, that we can have gallons and gallons on both sides, and since they cancel out, we can use gallons, we could use cubic meters, we could use liters. You can use this, since it's like just a percentage change, you can use any units you want on this as long as your units in respect to temperature are Celsius. So we're going to figure it out in gallons because we can. All right. Oops. That was bad. All right, so delta V is equal to, and then that was 950 E negative 6 per degree Celsius. My initial volume, I believe it was a 15-gallon tank. And the change in temperature is going to be, we'll just look for an absolute value in this case. That's 18 plus 11.7, which should be 29.7. And this is an average day in January between the two cities. I chose Yuma because it's one of the warmest cities in the United States. All right, so let's figure out our change in volume. See, Celsius cancels out, as you notice. And then that leaves me with gallons, which is what I want. So 950 times 10 to the negative 6th times my 15-gallon tank times the 29.7 degree temperature change. It's going to be 0.42 gallons, which is that's measured. That's definitely measurable. So the difference between the two would be 0.42 gallons. Once again, gas is, as far as I know, most gas stations that I've ever been to, it's held underground, so the ground should regulate the temperature to some degree. But this is if they kept it out, which in some cases maybe they want to in Yuma. So 42 or 0.42 gallons, and I want to figure out the cost, and that's $2.75 per gallon. And so I gave myself a little more room down here. That's good. So that's 0.42 gallons, and I know that's around $2.75 a gallon. It varies, but that's the number I used. And so I just take that, and then I times that by 275, and you're looking at $1.16. So interestingly enough, if they were to keep the gas outside and someone was to fill up, every week of the year, they would end up paying around $60.50 more for their gas in Yuma, Arizona than they would in Minneapolis. As it stands now, there is some change. Obviously, the ground is a lot colder, depending on how deep the tanks are, but the ground is going to be colder in Minnesota, so they do pay more in Yuma, but it's generally measured in the more penny region. Unless they secretly are keeping gas above ground, in which case they could really be taking it to their consumers. So, anyways, something kind of fun. Well, fun if you live up north, not fun if you live down south. So, those are the two cities. That's downtown Yuma, and that is Minneapolis. Two very different places. Okay, on to the next topic, which if you've taken chemistry, either in college or high school, you will know that, what specific heat is. Specific heat is the amount of energy needed to either heat up or cool a substance that is 1 kilogram, 1 joule, or Kelvin, since the change in Kelvin or Celsius, since the change in Kelvin is the same as the change in Celsius. Hence, the units are joules per kilogram degree Kelvin or joules per kilogram degree Celsius. So it could be either or. Joules. I usually write this as joules per kilogram degree Celsius, but it really doesn't matter too much. In any case, specific heat tells you a lot about the substance. Particularly if I know a substance specific heat, I can say, are you a good insulator? Are you a good conductor? Are you going to resist a temperature change? For example, if you look at these specific heats, the higher up the value of these specific heats, the better the insulator. Meaning it's going to take a lot of energy to either heat it up or cool it down. Water is a good insulator. Generally, we don't put waters like in our walls instead of regular insulation just because of the sheer mass problem. But if you look at some coastal cities in the north, they're a little bit more regulated due to the ocean, since the water tends to regulate that temperature since it resists the temperature change. Water ice, like regular ice, is 2,000 joules per kilogram degree Kelvin. It's also a good insulator. So if you think about the Inuit or the various other Native American tribes, they used to build houses literally out of ice. Yes, it's still cold, 32 degrees Fahrenheit, but 32 degrees Fahrenheit is still better than negative 32 degrees Fahrenheit. And so you can actually build yourself, or let's say you're in a survival situation, you can build yourself a snow cave. Because ice is actually a good insulator. We just don't know it as an insulator because our body temperatures tend to be around 98 degrees Fahrenheit. However, if we were an animal that had around 32, then it would probably be a great insulator. We'd use it everywhere. Then you start to get down into your conductors. These do not take a lot of energy to heat up or cool down. And notice there are a lot of metals. Iron, uranium, mercury, lead. All of your metals are going to be conductors. It's not going to take a lot of energy to heat it up or cool it down. A good example is, let's say I'm going to boil some eggs because I'm hungry. And I put a pot of water on there, and I put it on the stove in a stainless steel pan. And after 5 minutes, if I touch the pan, it's probably going to burn my fingers. If I touch the water, it may not. That's because the pan heats up so much faster than the water, because the water has a higher specific heat. So that's that's great about specific heat, is it could tell you whether a substance is going to resist that temperature change. And it can also tell you what substances you want to use for insulators, what substances you want to use for conductors. For example, I have been, for the life of me, wanting to get a blanket made out of like a metal of some sort or something with a very low specific heat. Because I don't like to be hot. And in the summer, if I had a nice cool blanket, it'd be nice. Think about it sleeping on a cold steel floor. It's not necessarily cold. It's just because it's a heat sink. It's drawing heat away from your body. And so yeah, anything that is conductor generally feel cool to the touch, and we'll kind of talk about that next chapter. I'm getting ahead of myself. But anyways, so the equation is Q equals MC delta T. Some books write it as TF minus TI. I just like it as MC delta T. It kind of sounds like a 90s rapper, more like 80s rapper, MC delta T. But anyways, it's easier to remember, and sometimes it gets confusing when you have your TF and TI, especially when you have multiple different thermal energies going on in you. So let's do a problem. Start off simple, work our way up. It takes around 4,100 joules of energy to heat up 100 grams of your refined uranium. If the initial temperature was 20 degrees Celsius, what is the final temperature of the uranium? I could use this TF minus TI. I tend to never do that. And I almost encourage you not to. And why is that? I think it's just easier to just do MC delta T, and then if it needs to be negative, make it negative. If not, make it positive. I think it's more physically makes sense to me, at least. So Q is our energy, and it's measured in joules, and that Q value is going to be 4,100 joules. And that's equal to mass, and so it's going to be 0.1 kilograms. In chemistry, you remember it's generally done in grams. But in physics, we do kilograms, so don't forget that. C is the specific heat of uranium, and that is going to be 116. And then the change in temperature, we're going to solve for that. And then I'm going to either add or subtract from 20. One thing to note, I always forget to say, and now I'm coming back to this is actually called the specific heat capacity. And there's also something called heat capacity. Heat capacity is just the specific heat capacity multiplied by the mass. I just generally drop off the word capacity because in some classes that I teach, we actually deal with both heat capacity and specific heat capacity. And if they miss one word that I say, it can literally change the meaning of what we're trying to do. So I will just simply say specific heat, but it is specific heat capacity technically. All right. Side note, fun times. All right, what we got here? We got 4,100. Divide that sucker by 0.1. Divide that by 116. And that gives me 353. I put gram when I was just talking about it. I just realized that. I'm sorry. Kilogram degrees Celsius. Kilograms cancel out. That's good. Joules cancels out, and you get a unit of degrees Celsius. So that's 353.4 degrees Celsius delta T. And then it started at 20. We said it's heating up. So I'm just going to add that to 20 degrees Celsius and say 373.4 degrees Celsius is the final temperature. Anywho, one other thing I just remembered, and it kind of left my brain that I was going to say. Oh, I said how it's the same in Kelvin as it is in Celsius. Well, okay, so this is all based off of delta T. And if I converted 20 to Kelvin, if you remember, your Kelvin is going to be, say, your Celsius plus 273. And so if I want to do that in Kelvin, that would be 273 plus 20. It's going to be 293 Kelvin. Remember, it's not degrees Kelvin. It's just simply Kelvin. And that would be my initial. And then the final temperature, 373.4. If I take 373.4 and I add that to, say, 273, that's going to give me 646.4. And of course, if I subtract 293, we get 353.4 Kelvin. So really what I'm trying to say in this point is that the change in temperature is the same in Celsius as it is in Kelvin. So you can use them interchangeably. What you can't use interchangeably is Fahrenheit, since remember Fahrenheit is 1.8 times Celsius plus 32, or 9/5 times, there's 19 different ways to express that. So either way, Kelvin or Celsius is the same, mainly because this equation asks for delta T, change in temperature. And because of that, it makes it pretty easy. All right, so let's step it up a little notch. All right, so let's say you heat up a 2.5 kilogram iron pot of 2 kilograms of water, 80 degrees Celsius. Assume the stove is 80% efficient and the average kitchen dining room volume is 179. I looked these values up, they're pretty close. How much does the air heat up? Okay, so basically, if you have a stove, what's the stove going to do? It's going to give off energy. Because you know if you cook something, it gets hot. Well, okay, so with the stove, it says that 80% goes into cooking your actual food. And it says that 20% goes into the air. Because we assume it's going to go into the environment. Okay, well, that's a little bit better. Okay, so then I need to find out, well, how much energy is going to be passed off to the air. All right, so we got Q is equal to MC delta T. The problem is we have two different things. We're heating up both the iron pot and the water by a change in temperature of 80 degrees Celsius. So what I really need is QT, which is quick. It is quick trip, but the total energy, which is going to be the energy of the iron. Remember Fe for iron, and the energy of the water, H2O. I think everyone knows that. So I need to add them up together. Okay, so let's find my QT. All right, so that's going to be M Fe C of Fe delta T, don't have to say what it is, I'll give you a second here, plus M of H2O plus C of H2O delta T. It's the same change of temperature, so I can pull it out to make it a little bit easier. So inside, that's just going to give me M phi C phi plus, I don't even know how to say that one, MH2O. Mahatu. Oh, that didn't work. Plus CH2. That one actually works. Ch2. Sounds like I'm shooting some laser space gun something. All right, now I get to plug in what I know. And that doesn't give me the answer yet. That just gives me the total energy used. Needed to heat up this crap. So I take my change of temperature of 80 degrees Celsius. The mass of my iron is going to be 2.5 kilograms. The specific heat of my iron, I actually don't know off the top of my head. So I'm going to look up here. 452. If you ever look up these values, you're actually going to see a wide range of values. It's around 450. Sometimes it says 440. It kind of depends on the experiment and the experimental conditions, but they're generally in the ballpark. The water, what did I do with water in this one? I see it not all over the place. It's always around 4180. I think your book uses 4186, which is what I used. So we're going to do that. And mass of water is, we said 2 kilograms of water. And 4186. Okay. And then closing parentheses. Okay. All right, so 2.5 times 452 plus 2 times 418, 4186. That's 4186. Okay, I multiply that by 80, and I get 760,160. Okay, now it says that 80% efficient. So that means it's going to lose 20% of the environment. So I'm going to multiply that by 0.2. And that means that of that energy, 152,032 joules of energy does not go into heating up your food, or at least the water in the pan. It goes just to the environment. We're assuming it all goes to air. The range will absorb some of it and, whatnot. But we're assuming that's all going to go to air for the simplicity purposes. Okay, so then how does that tell me how much the air heats up? Well, if I scroll up here, I see that air is 1,000 kilograms or joules per kilogram degree Kelvin. So I have the specific heat of air rolling down here. I have the volume, but I don't have the mass. So mass is equal to rho v. Okay, so we do know the density of the air and we know the volume, so we can do that. Okay, actually I want to do this. We're trying to figure out, well, we know Q is equal to mc delta T. M in this case is going to be rho v. So rho Vc delta T. Solving for delta T is going to give me Q over rho Vc. So I take my Q, 152,032 joules. Density of air, 1.29 kilograms per cubic meter. Volume is 179 cubic meters. And then specific heat of air, we decided was 1,000. All right. Taking my 152,032, dividing that by 1.29, dividing that by 179, dividing that by 1,000, gives me 0.66. So 0.66 degrees Celsius. So that's around a little over, about 1.2 Fahrenheit. Which makes about sense. I mean, if you're cooking something, it does tend to heat up the room, and 1 degree Fahrenheit is pretty reasonable. All right, moving on to the next topic is what if you have 2 different objects coming to, or fluids, really doesn't matter what. So I guess it can go with objects coming to a thermal equilibrium. Well, that's our next topic. It's conservation of energy in a calorimeter. Um, Basically put, you can add the individual energies of each one. Let's say you have, oh, I don't know. There's my cursor. Oopsie. There we go. So let's say you have coffee and creamer. And if you add the energies, you could say it's equal to a constant. More appropriately, we could say that the change in... Can't find my cursor here. The change in energy of my coffee plus the change in energy of my creamer is equal to a constant, and that constant is 0 if it's in a calorimeter. Basically, a calorimeter is essentially kind of a thermos. What it means is you're not losing energy to the environment. That all of the energy stays within that little confines of whatever you constructed. So basically, if I move EB to the other side, I get that the change in energy of my coffee is equal to the opposite of the change in energy of my creamer. Meaning that all of the energy, I probably should reverse that. So let's do that real fast. Let's change this one to creamer, because it'll make more sense here in a moment. And let's change this to coffee. Or I could have just moved my minus signs, but it's okay. Basically, all of the energy gained by your creamer is equal to all of the energy lost by your coffee. Now, that doesn't mean that the temperature change of your creamer is the same as the temperature change of your coffee, because that's not true. If I have a big, I don't know, 32-ounce thing of coffee, and then it's real hot, and I pour in my cold creamer, what happens is you gotta think of it as two separate substances, since they are. Your creamer is gonna warm up, and your coffee is gonna cool down, but they don't they don't have the same temperature change. Your creamer is going to have a huge temperature change, whereas your coffee, not so much. And so it's really the energies that are the same. The energy gained by your creamer is equal to your energy lost by the coffee. So that's basically conservation of energy, in this case, in a nutshell. The heat will continue to be transferred until some sort of thermal equilibrium is reached. Now, what that means... Oh, I didn't leave myself a lot of room here, but I can do this. Okay. Okay. So you got M1, C1, delta T... Well, actually, I'm going to write this out. I'm going to write it out bigger. TF minus TI1 equals M2, C2, TF minus TI2. Oh, I fit it in there. And I forgot my negative. Really didn't leave myself a lot of room here. Okay. So, because we know that Q, or energy, I said E, but it really doesn't matter. The energy is MC delta T. Well, if I were to multiply this out, that's going to give me M1, C1, TF. And notice that they both have TF because they come to the same final temperature, since it's in thermal equilibrium. Minus M1, C1, TI1 equals negative M2, C2, TF plus M2, C2, TI2. If I move everything positive on one side, so over here I'd have TF equals, times M1 C1 plus M2 C2. I just moved this to the other side and pulled off the TF. And on the other side, I'm going to get M1 C1 TI1 plus M2 C2 TI2. And then divided out, I have a final temperature equation. M1 C1 TI1 plus M2 C2 TI2 over M1C1 plus M2 C2. Basically put, this top little formula, I should have written it with more room. You can use, I mean, it's the same equation, it's the same formula. The only difference is this one's easier to solve for the final temperature, because if you use this top version, you're essentially going to have to do exactly what I did to extract the final temperature. So the upper one you would use to say solve for, like, you know, your mass or your specific heat, whereas this one you would normally use to solve for the final temperature. But it's the exact same equation, it's just different forms. Anywho, so that might make your life easier. All right, so let's say an unknown substance with a mass of 100 grams and initial temperature of 90 degrees Celsius is dropped into a container of ethanol at negative 5 degrees Celsius with a mass of 200 grams. Final temperature is 9.74 degrees Celsius. What is the unknown substance? All right, so we would not use the previous equation I just proved because we're looking for the mass of it. It would be hard because I'd have to extract the mass. So I just use the fact that M1C1 TF minus TI1 equals negative M2 C2 TF minus TI2. And so we know the mass of the unknown substance is 100 grams. We know its initial temperature, and we know it's the final temperature. And we know the mass of the ethanol, and we can look up the specific heat of the ethanol. Basically, we need to solve for the specific heat of that substance. So I'm going to solve this for C1 for now, as soon as I figure out how. There we are. So C1 is going to be negative M2 C2 TF minus TI2 over. This will be M1 TF minus TI1. Yay. All right, so let's plug in what we know. Since we have M2 and C2, the only C2 we have is ethanol, so M2 is going to have to be the ethanol mass. So that's going to be 0.2 kilograms. Specific heat of ethanol, I believe, is 2,400. But I don't remember. So I'm just going to roll right back up here and look for ethanol. Ethyl alcohol, 2,450. Close enough. All right, 2,450. So that's M negative M C2. And then final temperature is 9.74. So 9.74 degrees Celsius minus the initial temperature of the ethanol, which was a negative 5 degrees Celsius. We're minusing a negative here. And then I divide that by the mass of the unknown object, which was, I believe, 100 grams. So 0.1 kilograms. Final temperature, once again, was 9.74 degrees Celsius, and the initial temperature was 90. Okay. Calculator. Alright, so let's take a negative 0.2 times that, in parentheses, 9.74 plus 5 times 2450. Okay, and then divide that by 0.1, and then divide that by 9, in parentheses, 9.74 minus 90, close parentheses, and I get 899.9. And notice a couple things here that, well, actually, no, I was going to say something, but it's not really important. Okay, now that doesn't tell me what the substance is. So I scroll up to the top here. Let's look for something around, okay, aluminum, pretty much. 900, 899.9, close enough. So our substance is aluminum. Or from chemistry, Al. 3 plus. At least I think it's 3 plus. It's been a long time. All right. So Aluminum is our unknown substance. We can do this same thing we had to solve for mass, etc., etc. But that's something that's kind of handy is if you don't know what a substance is and you have a calorimeter, you can actually use it to figure out what it is based off of a table of charts. Now, there are sometimes a lot of different things at roughly the same value. Say your thing is not that accurate. 116 is not very far from 128. So it can only do it to some degree, but it does work that way. All right. Now we've talked about a substance in heating up or cooling down. We've talked about multiple substances heating up or cooling down. There's something else that happens. It's called the latent heat of fusion and vaporization, and that deals with substances freezing, melting, evaporating, condensing, subliming, etc. The latent heat of fusion is the amount of heat needed to melt 1 kilogram of a substance. So that's measured in joules per kilogram. It's not necessarily melt, it's melt or freeze in either direction. And then there's also something called the heat of vaporization, which is the amount needed to evaporate or condense 1 kilogram of a substance. The formula is quite simple. It is Q is equal to mL, where L is either going to be your latent heat of fusion, or it will be your latent heat of vaporization. M is your mass, so obviously it gives you energy. So you kind of have two different situations here. If a substance is melting or evaporating, it's going to take energy away from the environment. Kind of a good example of that would be, I believe, Native American tribes in the southwestern United States used to have like pots of like water, and then they would surround those pots with mud, and the mud, of course, would eventually dry off because the water there would evaporate within the mud, and when it evaporated, it actually took energy away from the water, which thereby cooled it off. So that was kind of something unique and neat that they were able to do to keep rather not hot water. I mean, we're not talking a huge temperature change, but definitely cooler than normal. And so they utilized that. One thing that utilizes melting is actually in your book. It's PCM is what they're called. Basically, substances, little microplastics within like your winter clothing, will sometimes melt to take energy away from the body. So that's like, let's say you're snowshoeing and you get a little overheated, then the substances inside the like jacket you have would melt and take energy away from you, thereby keeping you cool. So those are two little instances where they utilize this. If the substance is freezing or condensing, it's going to put energy into the environment. That same PCM I was talking about will freeze when you're not doing anything, thereby transferring energy back into you so that you can keep warm. There's another application of freezing that I'm going to do here in a little bit. It's from a problem from the book, but I think it's kind of cool. Anywho, so let's do some problems with this. All right. How much energy does it take to melt 500 grams of water ice? The latent heat of fusion is 3.35 times 10 to the 5th joules per kilogram. Wow. Degrees Celsius. Why did I not catch that? Sorry. I'll correct it on the one that I give you. As long as I'm going to put a little reminder to myself so I don't forget, but that's bad. Correct. L. That'll be good. Okay. Anyways, it's supposed to be joules per kilogram. Why I did that, don't even ask. Okay, so we want to know how much energy does it take to melt that water ice. So, okay, I'm going to come down here and do it, if I can find my cursor. So it just basically, it's just Q equals ml. And so I take the mass, which is 0.5 kilograms, and the latent heat of fusion of water, 3.35 e to the 5th joules per kilogram. That's why it's not joules per kilogram degrees Celsius, because then you'd have a weird unit. And so it's basically half of that. Getting back to Mr. Calculator here. So 0.5 times 3.35 E5 is going to give me 1.675 E5. Find Mr. Cursor. Where did you go? There you are. Okay. How much energy does it take to change 500 grams water into steam? So these are all pretty simple. We're kind of leading to something here. So that's also going to be ml. Same 0.5 kilograms. And it's a much larger value, 2.26 E6 joules per kilogram. All right, so 0.5 times 2.26 E6 is going to give me 1.13 E6. Notice it takes a lot more energy to either convert water to steam or steam to water than it takes to either freeze or melt the same substance. Basically put, when you think about the energy of the molecules, there's not a lot of energy in a solid like water ice. A little bit more energy in a liquid, it can move a lot better. And then in a gaseous state, it's way more energetic. The particles are moving way faster, et cetera, et cetera. So you can kind of think of it that way, but it does take a significantly more energy to vaporize a substance in general than it does to freeze it. Or sorry, it would be melt it would be the right word to use. Well, the third one says sublime, ice to steam. So this is a little bit different. If you want to take it straight from ice to steam, you would have to have 3 Qs. So we'll go back to Qt. You would have Q1, which is going to the energy needed to change it from a solid to a liquid, plus Q2. Then you'll have to account the energy that needs to take it from 0 to 100 degrees, because that's the range under STP of liquid water. Then you're going to have to account for the energy needed to get it from a liquid to a gas. So 3 different Qs. All right, well, a couple other things. We already know what Q1 is. We already figured out the energy needed to change from a solid to a liquid. That's 1.67 E5. The energy needed to heat it up is just going to be MC delta T, which is going to be 0.5 kilograms. 41, I think it was 86 joules per kilogram degrees Celsius. And then 100 degrees is the temperature change. And we already know Q3, the energy needed to change it from a liquid to a gas. That's 1.13 times 10 to the 6 joules. I need to move my pad up so I can write a little bit better. Sorry about that. All right, so 1.67 E5 plus 0.5 times 4186 times 100 plus 1.13 E6 is going to give me, looks like, roughly 1.5 million. We'll just call it good there. How about that? So the bulk of the energy needed to sublime something is to vaporize it, essentially. So, fun. Anywho, there are some applications and some problems where you're going to have to do multiple different Qs because you're going to have to figure out the energy needed to change its substances plus energy needed to heat it. For example, if we would have taken ice at negative 50 degrees and gone up to steam at 150 degrees, we would have to account for the energy needed to change as solid from negative 50 to 0. At 0, it's going to melt, and you can kind of think of it as a graph. So basically put, it would stay as ice. Let's say this is negative 50, and we're going to go to 0, and then we're going to go to 100, and then we're going to go to 150. It will go up, 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 up as a solid, and then at 0 it kind of levels off because it's got to change its phases. And then it's going to go up again, probably at a steeper rate since its specific heat is higher. And at 100 it levels off again, and then it's going to go up again. because it levels off because during a phase change, they cannot change temperature. The substance can't change temperature. It can only change its phase at that point. And so you could get to essentially have 5 different Qs. In this case, we only had 3. Well, let's combine conservation of energy with latent heat of vaporization, fusion, etc. Let's say you have 500 grams of silver is heated from 0 to 2000 degrees Celsius. The melting point of silver is around 962. And let's say you have a 500 watt special oven that's able to do this. Just assume. How long will the oven have to run? The solid specific heat is 230 joules per kilogram Kelvin. And assume the liquid specific heat is 200 joules per kilogram Kelvin. And the latent heat of fusion is 88,000 joules per kilogram. I said assume the liquid specific heat. I had trouble finding that value. And so I chose that one. Called it good. Wasn't really sure. So, couple assumptions here. All right. So what happens here is we know our silver is heated from 0 to 2000. Let me kind of write this out up here from my cursor. So it's going to go from 0 to 962. And it's going to do this entire thing as a solid. Right? Then it's going to change phases from a solid to a liquid. And then it's going to go from 962 to 2000. And then that's as a liquid. So it's very similar to the last problem. But it's saying how long we have to run the oven. What's that mean? Well, if you recall, power is equal to work over time. In this case, our work is energy, thermal energy. And so it's really just Q over T. And so really what we get is PT is equal to Q, or I probably wanted to say that T is equal to Q divided by P. So if we find our thermal energy, we could divide it by the power, and the answer is going to be in seconds and how long we need to run it. So let's do that. All right. All right, so M1. All right, so first it's going to be as a solid, so it's changing temperature, so it's going to be M, and I'll call it CS for solid, delta TS for the solid change of temperature. Then it's going to go through a phase change, so that's going to be ML. Then it's going to be as a liquid, so we're going to go MCL delta TL. And that's going to be our total Q. We can pull out the mass to simplify this a hair. So CS delta TS plus CL, L plus CL delta TL. And so I'm going to go ahead and do that. I think I had a half a kilogram. Is that right? Yeah, I did. My handwriting is getting worse, I feel like. I'm sorry. All right, so 0.5. And then I'm going to multiply that by my solid specific heat, which was 230 joules per kilogram degrees Celsius. Because remember, change in Celsius is the same as Kelvin. But when I looked it up, it gave it to me in Kelvin. And then times the change in temperature, which would have been 962. And then plus the latent heat of fusion, which looks like 8083. And then plus the liquid, which was, I said 200. I'm going to run out of room here, sorry, so I'm going to have to drop my units. And then change the temperature. So it's going to go from, where do I write it? 962 to 2000. So what? That's like 1038. Yeah. Yep. Close. All right. Probably should have put that on the next line. Would have had more room, but whatever. So 230 times 962. And then I add that to 88E3. And then add that to 200 times 1038. 8. and then close, and then multiply all that by 0.5. So that's going to give me, I'm going to write the whole number here. I usually don't like that, but I will. 258,430. And so I said, remember, I could just divide that by the power, which is a 5,000 watt oven. Remember, watt is a joule per second. So joules cancels out and you get second. So I divide that by 5,000, and I get around 51.7 seconds. So, kind of a fun application, combining something from the past with what we're doing now. And I think the very last problem does something similar to that. All right, well, this is from the book, but I really like it. At least when I was a kid growing up, I was always fascinated with why they would water trees down before a freeze, like in Florida, like orange trees. Well, that's because they're trying to keep them from freezing, which just was bizarre to me. I mean, why would you freeze something to keep it from freezing? Well, this problem kind of addresses that. To prevent frost damage, fruit growers protect their crop by spraying it with water when temperatures are expected to go below 0 degrees Celsius. When water freezes, heat is transferred to the plants, as I explained earlier with the jacket example. Suppose a grower sprays 7.2 kilograms of water at 0 degrees Celsius on a fruit tree. So it's already at its freezing/melting point. How much heat is released by the water upon freezing? Okay, so I think I gave myself an extra page here, but I'll start here because I need to do this. All right, so it says just freezing. So we're not going through a temperature change, so it's just going to be ml. And we know that the mass is going to be 7.2 kilograms. And the latent heat of fusion of water is 3.35 E5. So, 7.2 times 7.2 times 3.34 E5 is going to give me 2,404,800. I think I'm just going to say 2,405,000. Okay. So that's how much energy is going to be transferred to the plants. And then it says how much would the temperature of a 180 kilogram tree rise if it absorbed the heat. And the specific heat of the tree they gave you in the problem is 2,500 joules per kilogram degrees Celsius. Okay, so now we need to use MC delta T, with the mass being the mass of the tree. Specific heat is given as 2,500, so we're looking for delta T. So, okay, so it's Q over MC is equal to delta T. Roll down here where I got some more room. So I take that Q, so 2,405,000, roughly, divided by the mass, which is now 180 kilograms, and then the specific heat, which is 2,500 joules per kilogram degrees Celsius. Joules. Forgot my unit up top. Alright, I'm just going to use the number it gave me. Divide that by 180, divide that by 2,500, and you get around 5.3. .3 degrees Celsius is actually like what, 8-ish degrees Fahrenheit. That's pretty significant. So by actually spraying the trees, and then when the water freezes, it transfers the energy to the fruit, and the fruit ends up heating up, so it keeps it from actually internally freezing, which is still fascinating to me why they do that, but it works. So, and then the science is behind it. So, anywho, something always fascinated me as a child. I think I have one more problem. All right, last problem. Kind of alluded to this and promised this earlier, where we would do a problem that kind of combines different types of energies. Here it is. Let's say you have a, this is from the book, by the way, 42 kilogram block of ice at 0 degrees Celsius is sliding on a horizontal surface. The initial speed of the ice is 7.3, and the final speed of the ice is 3.5. Assume that all of the heat generated by the kinetic friction goes into the block of ice. Determine the mass of the ice that melts into water. Okay, so basically what's happening is your ice is undergoing a change in kinetic energy, which we can do, if you remember, is going to be 1/2 of mv squared minus 1/2 of mv naught squared. Now, it's saying assume that all that heat generated goes in to the block of ice. So all that kinetic energy is going to go into thermal energy, which we know is Q, which we know is going to be mL, where L, of course, is our latent heat of vaporization. And so what we're looking for is that mass of water that's actually going to melt. And by the way, I should have denoted that this is the mass of melt, so we'll say mm, because it's a different mass. Because this is going to be the 42 kilogram mass, whereas this is going to be what we're looking for, how much actually melted. So let's go ahead and do that. All right. I can pull out my 1/2 m. I'm going to make this a little bit simpler. So that gives me 1/2 m v squared minus v naught squared is equal to m sub m L. Let's do that. All right, so 1/2 of 42 kilograms. Final speed is going to be 3.5. Initial is 7.3. Minus 7.3. And then all divided by the latent heat, which is going to be 3.35 times 10 to the 5th joules per kilogram. Yes, it's going to be negative. We're not so much concerned with the negatives because your book doesn't really go into it so much. We're just kind of assuming the absolute value of it. So just kind of let you know there. But 3.5 squared minus 7.3 squared. And then I'm going to times that by 42. And then I'm going to times that by 0.5. And I'm going to divide that by 3.35 E5. And I get a really small number. And remember, we're more looking for an absolute value here, so let me be more clear. Oopsie. Close enough. And so I get around 2.57 times 10 to the negative third kilograms, or 2.57, yeah, 2.57 grams. Which makes sense because a block of ice sliding, it's 42 kilograms, you're not going to see a lot melt. That's kind of consistent with what we would actually see. That is it for chapter 12. Dang it, I can't get my chapter straight. And I will try to release chapter 13 whenever I get an opportunity.